Hello. Does this whoa? Wait, I cannot hear myself. That is not good. Why can I not hear myself? Let me see. I should have an audio mic. Wait, no. Yeah, it should work. I'm so confused. Can you guys hear me? That is maybe the next question. You guys should be able to hear me. So why is it I cannot hear myself? Um, I'm confused. Let me see. Hey, right, you guys can hear me, yeah? I'm almost completely sure you guys can hear me because that's what OBS is saying. And and OBS is also saying that my what is it called? OBS is also saying that I have a monitoring device. Um, so what if I do this and then I don't know apply? I still cannot hear myself. Oh, this is this button that turns on and off the monitoring. Okay. Well, it's what it is. Okay, good. Let's get on with the lecture. Okay, yeah. Your face cam stream, I know, because well, I mean, soon enough I'll go back to the PNG tuber thing, but for now, since this is actually like professional things, then that's actually a Sorry, I'm just trying to stall until my what is it called? Until I can make my tea. The water, what is it called? The kettle is almost boiling. So yeah, might as well chat a bit, right? Because this is how streaming is, anyways. Yeah, so I was actually out there today. I took a very long walk, so it was yeah nice weather. Like temperature is finally getting reasonable, and I finally had my tea. Sorry. Yeah, let me just quickly make this, and then we can start. Yeah, so Qiskit programming. So this is basically, like how to build, like how to program, like how to write quantum programs, basically. And the lecture is supposed to be 75 minutes long. This is basically because the professor is traveling, so I'm supposed to be giving one of the lecture for him. Why is this loud? I need to fix the sound balance. Otherwise, I cannot hear myself, and that would be bad. You guys can hear me, and you guys cannot hear my BGM, of course. Yeah. Okay. Good. Anyways, let's actually start. Yeah. Okay. So I don't know. Let's just jump right into it. This is the second lecture in the series. Anyways, you guys might not have watched the last one. Okay, so basically we are going through Qiskit, which is basically a programming, a library to write down quantum circuits. And in terms of setup, it's basically similar as usual. Basically, you just have this requirement.txt thing, which basically this is like the Python packages that we're using. So to set things up, basically you could just, maybe create a virtual environment and you select it and then you install it. But maybe I won't spend too much time on this because I'm just going to assume that you guys either already know Python or can learn it. I mean, it's like what I said last time, right? We are programming the three quantum computers here, so Python compared to that should be a piece of cake. So yeah, um, and in terms of dependencies, basically, this is also the kind of boilerplate that we don't really need to care too much about. The only thing is this, basically this solution key. So how this lecture works today is, as you will see, that a lot of things are like this Jupyter notebook, like this lecture note, is technically incomplete. And the homework is to, because this is actually for a college class. So the homework for the students, not for you guys, unless you guys can also do it. Why not, right? Yeah, the homework will be fill in the missing pieces for the textbook, for the what was I saying in this notebook. But for the sake of a lecture, I would just import my own solution key so I can actually finish the lecture today. So I will, run this, assuming this actually runs, and then it's taking a minute for some reason. If it actually crashes or burns here, I'll be very sad, you know. I mean, I won't. I would just restart VS Code since I will have to. Why is everything so scuffed? Okay, good. Now what? Now we will try this again. Detecting kernels, okay, and then I will run this. Is it going to work? Please work. Okay, good, perfect. Now it works. Okay, so first of all, to create a quantum circuit, basically, I mean, we actually already went through it in the last lecture, so we are not going to go too deep into this. But basically, this is just how the usual object-oriented programming thing works. Basically, you create a quantum circuit object. This is, you know, I mean, this Python, so you don't need like the word new or whatever. Right? Yeah, I think that's how Python works. Don't remember how to write Python. Yeah, why do you not need a word new in Python? Probably because it's not C++. Anyways, okay, so you create an object and then you have here I have quantum circuit of the first parameter is number of qubits and the second parameter is number of classical bits. So I have 2 qubits and 2 classical bits. And then I have a Hadamard gate. I have a CNOT here, and I measure my 2 qubits into my 2 classical bits. So this is my list of qubits, and this is my list of classical bits, like where to store the measurement outcome. And then you can draw the circuit. So there is kind of that, nothing super exciting yet. And then once you have a circuit, you can also run the circuit. In general, you will have to run on the actual quantum computer, but then if you don't have that many qubits, actually I covered this last lecture as well. But this laptop is not secretly a quantum computer. I'm not connecting to any other quantum computer on the network either. Basically, I just do a simulation because you know 2 qubits 2 to the 2 power second power is 4, so it's 4 by 4 matrix or something like that, which is not you mean, yeah, this is obviously doable. Anyways, yeah, I mean, all of this is reviewed, so I'm just going to like handway through this. Yeah, so first homework exercise is to draw a circular dust list, create your C state, and then flip the first qubit and measure everything. So here you are supposed to be filling in this homework.py, which has this thing defined in there. I will not show the solution here, but basically your result should look more or less like this, where you have this part that creates a GHZ, and then you flip the first qubit, and then you measure everything. So let's simulate everything as before. So this is just boilerplate code. You don't have to worry too much about it either. Basically, you have a simulator and then you do sim.run, and then here's your circuit and how many times you want to run it, and then you have result, and then you know you can just print the result. So yeah. So notice anything strange? Sorry, the allergy is killing me. For the real deal, I really need to have some allergy medicines. Yeah, that was actually what happened earlier today. So when I was taking a walk, my allergy was so bad. And I got some groceries, but funny enough, indoors is even worse. Anyways, yeah. So the first qubit here, so you see my X gate is applying the first qubit, so I should be getting this state. But then it seems like what is being flipped is the actually last qubit. So it turns out the first qubit is actually rightmost one. So this is called a little endian bit order. Basically, a least significant bit is the first one. This is just how Qiskit decides to do things, so you need to keep in mind. Okay. So now let's actually build some meaningful things. So first of all, super dense coding. I mean, I would just assume knowledge of this. So maybe I can just read this out quickly. So recall the setting of super dense coding. So you have 2 players. Maybe I should say that. There are 2 players. Alice and Bob, and then basically Alice and Bob each hold one half of EPR pair. Alice wants to send 2 classical bits these two classical bits XZ to Bob, but she can only send 1 qubit. So, and then Alice operates on her half of the EPR and sends to Bob. And Bob decodes his 2 qubit to recover, instead of star, let me just do X prime, Z prime, because star in cryptography looks like it's been attacked, which is not the case. Okay. So how do you do this? Well, basically, again, just as a quick review or summary, for, I don't know, at least for the for students, for the college class, for you guys, you're just along for the ride. So either you know this or you, yeah, I mean, I would just assume you guys know this, or we can chat about it some other time. But yeah, basically, the idea is that um you consider this, basically just kind of work out math, and you realize that if you consider this circuit that prepares the EPR pair, then you have these results. Basically that if you apply this on all 4 possible inputs, you get these 4 outputs. And you see that these are all some gate apply on the EPR pair. So that basically means that if you apply the right gate here and apply the right and then apply U, then you get this this data back. Yeah, sorry, I'm just being really hand wavy here and not really explaining it, because this is again, like, this is a programming lecture. Yeah, I mean, I would be explaining this on the whiteboard if I'm actually trying to explain the theory, but now I'm not. Yeah. Anyways, the long story short, Alice should encode her qubit by applying this operator, and Bob should decode the result by applying U dagger and measuring the result. Okay. So Alice's action is left as an exercise. Basically, she encodes her qubit by applying this. So that basically, this is the circuit here. If X is 0 and Z is 1, then she applies a Z gate. And if you have 1 1, then of course, or 1 0, then this is basically just like this. And 0 0, basically Alice does nothing. Yeah. Okay. So, and for Bob's, basically, this is a homework exercise as well. But he basically, as I was saying here, Bob should do U dagger and measure. So U dagger means you apply this in reverse. So you do C naught and H. So you do C naught and H and measure. So this is what Bob should be doing. And then basically now with Alice and Bob's action, now we can actually put the entire super dense coding thing together. Yeah, maybe sure. Or maybe fine, let's read this first. So basically there are 2 qubits, because that is a 2 qubits that is shared by Alice and Bob, and I want 2 classical bits because I want to measure them. So you prepare the EPR, which is basically the standard thing, Hadamard and CNOT, and then you put Alice a what is it called? Alice operation. This is basically some boilerplate code that you just kind of have to know. But maybe let me format this a little bit better so it's like at least a little bit easier to read and easier to explain. Okay, so basically Alice circuit is contains only 1 qubit and no classical bit. So basically, I want to say that okay, Alice does her stuff on qubit number 0. And then for Bob does things on 2 qubits and 2 classical bits. So I want to say that I start with this circuit. I compose Bob's action, which is basically and where do I want to apply Bob's action? Well, I want to apply it on my 2 qubits and the 2 classical bits in that order. Okay, and then this basically gives me this. Actually, maybe if you draw it, then you just kind of get this over here. you prepare EPRs here, and then here is this Z gate is Alice action, and everything from here to here is Bob's action. There's also this nice thing that if you do QC dot barrier, then it makes the drawing a bit easier to read. So let's try that. So if I do QC dot barrier, basically just just draw lines between different parts, and you can kind of see like, yeah, this is prepare EPR, this is Alice part, and this is Bob's part. Yeah. Okay. Anyways, so let's simulate a circuit and check if the result is correct. So super dense 01 is the so here's I pass this as input, so this is just Alice input now. So basically because Alice takes two input, and then this is just hooking everything together. So you have this, you run this, and then you see the measurement outcome here is always 01. So that means basically a super dense coding's output is kind of what you expect. Yeah. Sorry. Because you start with the input, at least start with the input 01, and this 01 is kind of what Bob gets at the end. Yeah. Or is it? Well, I'm getting a little bit confused. Because shouldn't the thing be little endian? If a thing is little endian, then how do I I feel I might have a bug. I feel like it should be 0, 1 is 1 is x I really? No, 1 is yeah, I see the problem here. Yeah. 1 should be, wait. Yeah, this thing is a I think I have I think I have a bug. Let me see if I should fix, how do I fix this? If Alice wants to send 01, then do I show a solution? I guess I do show a solution for now, just for the sake of fixing it. Okay, so super dense Alex. So, oh, I want to switch the order, right? So Z and X. Wait, is that true? This is really confusing. If I want to send, no, I think it's the coding side that has to be fixed. So this is X is 0, Z is 1. So then basically X is 0. What's going on here? Huh? Well, I guess this is lecture rehearsal, so things are expected to go wrong, but I did not expect things to go wrong so quickly. Just like this, there's this nonsense. Let me just stare at this then. So, getting so much blackboard blindness right now. I feel like this shouldn't be this hard. Let's say if, fine, okay, maybe this is this part that I kind of hand wave over that actually should not have been hand wave over. So if Alice wants to send a let me see. So if Alice does 01, then Z is 1. So Bob should be getting this, which means I think the math actually works out, because this is a because there's this endian thing. Yeah, okay. So I mean that the result is right just because the how do I even, okay, so the thing is that X actually corresponds to a second bit, and Z actually corresponds to a first bit. But then because endianness, so then basically this just gets flipped and things are, so 01, which is Z, is actually no 01 actually matches with 01. Long story short, so this is, this is as expected, just because things are actually getting flipped twice, and then things are correct again. Yeah. I think I'll try to fix this offline because something is strange. Anyways, and if you try all four of them, then all four of them should also give you the expected result. You know, like 0, 0, basically. I mean, this is basically just putting this in the loop body and running for all four, and then checking that checking the checking this is actually the same as this, which is fine. Yeah. Okay. So now, next thing is the quantum teleportation. I know this is explained really badly. I'll fix it. Either rehearse this again or let's do better in the actual lecture. We'll see. Or I mean, I might even be fixing this right after, but now I just want to keep going so I can kind of have an estimate on how much time this lecture is. Okay. So quantum teleportation, which is probably easier for me, I don't know about for the students, but because this is what I actually work on, that I know how this works a little bit better. But basically, the idea is that you have quantum teleportation circuit, and this is what we are trying to do. We are trying to implement this. So okay, so how do we do this? Well, basically, Alice and Bob shares an APR pair, which will correspond to. Can I? Does it let me do this? Yeah. Okay. So Alice and Bob shares an APR pair here, and then Alice applies the operation, basically this funny circuit, and measure her qubit to get the outcome that X, and sends it to Bob. And then Bob basically applies this on his half of EPR pair to get a result. Okay, so basically, let's start with Bob's operation. So you see, this is actually what we call classical control, which is a little bit different from earlier, where okay, so earlier Alice gets two classical bits and just runs different circuit, depending on which one is her input. But this case, what we want to do is a little bit more complicated because the Bob's operation actually, we because we are already halfway through a circuit, so Bob cannot just decide to kind of run a different circuit. But this kind of like classical control, this if else, has to be what is it called? Has to be encoded inside the circuit itself. So what I mean is basically, let me just draw this and you will see. Basically, we had to do something like this, that we have some classical outcome, and then we need to say that condition on if the bit 0 is 1, then you apply this, or if the bit 1 is 1, then you apply this. By the way, this 0x just means the thing is in hex, like base 16. But if it's just if what you have after the 0x is just either 0 or 1, then this 0x can be ignored for now. It's not important for now. Okay, so anyway, so this is what Bob does in what is it called, in teleportation. So let's actually see how this is built. So for classical control, for whatever reason, Qiskit wants you to actually write down the registers instead of just use numbers for qubits. So basically, we want to say that, well, Bob has a quantum register and a classical register. Classical register is 1 qubit because Bob basically has only 1 qubit, which is his half of EPR, and then Bob gets 2 classical bits from Alice. So this is 1 and this is 2. The length of it, I mean. How to construct this, you will actually is right here. The way to construct this, literally just call constructor 1 qubit, 2 qubit size. Okay. And then basically you just say that, okay, you create your quantum circuit as before. And for this classical control, the syntax is basically with QC if test. QC is just my quantum circuit. If test, I'm calling a method here. And then I say I check if my classical bit is this value. Maybe I should just write 1 here. So if this is 1, then you do this. And if this is 1, you do that. So yeah, if the 0 bit is 0, then this is zx, so this is z, and this is x. If z is z, then you apply this. If x is 1, you apply that. Yeah. I know I'm doing this to actually this is not, it's not even out of order. It doesn't really matter because Pauli's anyways, yeah. Maybe I will brush that under a rug. So anyways, I have this. Yeah. Okay, and Alice operation will live as a homework exercise, but basically, the idea is that Alice has two qubits, two of them, one of them being her input, the other one being her EPR half, and she has two classical. I mean, for classical register size, you basically just pick it to be whatever number, like as many bits as you need. In this case, we need two, and then you will get something like this. Yeah. Because this is just what you do interpretation, and so this I would just hope you guys remember how this goes. Okay, so now let's actually also check if the entire picture fits together. So okay, so now let's actually first create all the registers. So in the teleportation experiment, we have 3 qubits total, yeah, because we have 3 wires, 1, 2, 3. So I have 3, and then Alice qubit is the first 2, and Bob's qubit is the last one. Here I'm using a slice because, well, you'll see, yeah. And Alice, well, there are 2 classical qubits, so I define this classical register of size 2. And we also want to check if teleportation succeeds. You will see this later, but I'm just going to define this for now. Define a single qubit thing. Basically, later in the experiment, we will check if the teleportation restored matches Alice's input. How do we check? You'll see. Okay, so now Bob basically, okay, so now I just want to say a little bit about this line. Why this is 2 colon and not just 2, because this is a Python thing. It's basically a slicing operator. You can look it up if you don't know what it is. But basically, yeah, if you slice the qubits, then you get a list. But if you index, you get a single qubit. And so these two are actually different things. And for whatever reason, Qiskit likes this one more than this. So this is what we want to write. Okay. So now let's actually put the entire interpretation experiment together. So basically, let's say that we have what? Okay, so we start with this, our 3 qubits, and we start with our 2 classical registers. So this thing is what we call var arg. Basically just put in however many, just drop all your registers in here, you'll be fine. Okay, and then we want to prepare Alice's input. Let's say, oh, I could be putting this here instead, maybe a bit easier to read. Well, okay, first of all, we prepare EPR, which is maybe a simpler part, just as before, Hadamard C0. And then prepare random inputs for Alice, yeah? So to prepare random input, basically we just do a random unitary, and we apply on Alice's, apply the 0 qubit, then this would become random, state, and then we teleport the random state, yeah? So teleport, basically we do the same compose thing again. Oh, why? I don't know why my indentation is off. Whatever, yeah. So basically, oh, maybe this is a bit better if I did this, yeah. Okay. So Alice does things first, yeah. So Alice basically does her part of the protocol. So this is the circuit we had above, yeah, teleport Alice, which is a this, yeah. So we do this first. And of course we need to say what qubit does this act on. So it acts on this qubit and it acts on this classical bit. Okay. And then it's Bob's turn. So we also do this, and we also say what does Bob get. Well, Bob gets his qubit from here, and he also gets the classical bit, which is Alice's measurement. This in place is always true. This is a some historical reasons. This is just a technical, like historical baggage kind of thing, like backward compatibility, whatever. I mean, you can read documentation if you want to find out the reason, but for now, if you are not interested, just set this to be true, you'll be fine. Okay, and then basically that is the entire teleportation. So now we check if teleportation is successful. If it is, then output will be U apply on this, yeah? So, which means if we undo U and measure, we'll get 0 back. So let's see if that's true. So we do U adjoint, which is, a U inverse on the teleportation outcome. So we apply U dagger, and then we measure it. And if it's successful, then the result will be 0, yeah? So let's first figure out if the circuit looks right. I'm assuming it actually runs. Why is it not? Why is it always taking? It's not supposed to be taking this long. Okay, good. Yeah. So you prepare your input, you prepare your EPR pair, and then Alice does her stuff here, and Bob does his stuff here, and then you undo the preparation. So you dagger, and then you measure, and then the result should be 0. So let's simulate this and see if that's true. Okay. So because again little endian thing, so this is the last qubit. Yeah, I mean last classical bit. And the last bit is on the left. So see, my bit is always 0, which means the teleportation is successful. And you also see that the teleportation correction, which is Alice measurement, this is uniformly random. So for all 4 possible outcomes, you get a about equal probability. That is, I mean, I'm not sure if this is covered in lecture, but you should expect this because, well, I mean, there's something has to do with no cloning theorem. Like this cannot depend on the input and stuff like that. Actually, that is maybe too hand wavy. So I would just say this is uniformly random and hand wave. Why? Anyways, yeah. Okay, so that is quantum teleportation. So now let's move on to entanglement swapping. So basically, there are no new building blocks required for entanglement swapping. So basically, all of the operations are just homework exercises, but I can still kind of say what we expect from you, from the students, not from you guys who are just watching the stream, but from the actual students of the college class that I'm lecturing to in a couple of days. Yeah, sorry, I'm just trying to move some stuff. Okay, where are we? Kill my train of thought. Okay, yeah. So for entanglement swapping, here's a setting, just to jog the student's memory, and I am also using a same very terse explanation here because again I want to check. I want to see if my lecture is exactly 75 minutes long or it is not like way under or way over. Okay, so there are 3 players: Alice, Bob, and Charlie. Alice and Bob want to share EPR pair. Alice and Bob cannot communicate with each other's. Oh, maybe I can combine these 2 points, but they cannot communicate with each other. I think it's singular, right? Okay. Alice and Charlie share an EPR pair and can communicate classically. And Bob and Charlie share an EPR pair. We don't care if they can communicate. Okay. Now the theory reminder. So basically, like how this works. Suppose we have 2 EPR pairs in 4 qubits. Qubits 1 belong to Alice, 2 and 3 belong to Charlie, 4 belong to Bob. Yeah. So which is what we were saying earlier. 1 2 is EPR pair. So basically 1 2 qubit 1 2 is the EPR pair shared by Alice and Charlie. Qubit 3 4 is the EPR pair shared by Charlie and Bob. Yeah. Okay, and here's what we need to do in entanglement swapping. Because it's covering some lecture before, so as in covered in the lecture that I'm not giving, but given by the actual professor of the class. Basically, Charlie needs to apply C naught and Hadamard on his qubit. Hadamard 1, as in Hadamard on his first. This one is actually used. Hadamard 1. So Hadamard 1 on his first qubit, which is the second qubit globally, is confusing, I know. But anyways, so let's say how quickly go through a math on what happens here. So we start with two EPR pairs. We basically expand this out, and then we apply a C naught. Um, this does not change. This does not change. This flips the third bit, and this flips the third bit. Yeah. And then we do a what is it called, a Hadamard. So that this becomes this two, this becomes this two, yeah, and this becomes this two, and this becomes this two, yes, because Hadamard 0 is 0 plus 1, Hadamard 1 is 0 minus 1, yeah, okay. I mean, I'm ignoring normalization here, but that is just how it is. Okay, and here I'm just grouping everything up. I'm just kind of like rearranging everything, so this is equal. Here I'm basically arranging the things that is arranging based on Charlie's qubits. So for example, this two term both have 0, 0 for Charlie's qubits, and this two term both have 0, 1 for Charlie's qubit, which is 2 and 3, and this has both 1, 0, and this is both 1, 1. And again, like maybe I should just say plot me, or I don't know, but these are equal. Yeah. And then I relabel the qubits. I basically just kind of move this 0, 0 out, and then the remaining qubit is 0, 0 plus 1, 1 here. And this is, I move this 0, 1 out here, and then this is 0, 1, 1, 0. Yeah. Basically, I just do the same thing here, and then I basically say that okay, now this is just normal EPR pair, and well, this is 0, 1 plus 1, 0, which is x1 apply on EPR, and this is z1 apply on EPR, and this is x1 z1 apply on EPR. So that is just kind of what you have after Charlie applies C0 and H0. I mean C0 and H1. C0 and Hadamard. Yeah, indexing is hard. O51 errors. One of the most common programmer errors. Anyways, yeah. Yeah, what was the meme again? Like the yeah, I don't remember the actual meme, but the actually, yeah, you know what? Uh hard for programmer off by one meme, I guess. What was it? Oh yeah. They are like what? Yes. There are two hard problems in computer science: cache invalidation, naming things, and off-by-one errors. Yes. Yeah. Anyways, there's that. Yeah. Okay. Back to being productive. Okay. So yeah. So you measure this first register. Yeah. So then, if you measure 0, 0, then Charlie's then Edison Bob shares this. If Charlie measures 0, 1, then Edison Bob shares this and stuff like that. Yeah. So basically, next Charlie just sends this M to Alice, and Alice just using this maps the state back to EPR. Okay. So this is kind of what we want to do here. I hope there's no like endianness things, like bit order things. I don't think so. Anyways, yeah, Charlie's operation is an exercise, but basically it's just C naught, Hadamard, and measure. Yeah, so here's C naught Hadamard measure. Yeah, so two qubits, two classical bits, nothing too exciting here. Same with Alice and Bob's operation. Actually, Bob does nothing. Alice's operation is basically take the measurement outcome and say if the first bit is 1, then you apply a Z. If the second bit is 1, you apply a X, which is exactly what it is, right? If the first bit is 1, then you apply X. If the second bit is 1, you apply Z, which is, yeah, I feel like there is still like really funny bit ordering things. How much should I be worried? Maybe not much. Yeah, maybe this is fine. Yeah. Yeah, I feel like as long as a bit order thing bites me once, I'm just going to be very, very cautious of it. Anyways, yeah. So first bit is what's this? So math says that the first bit, which is the one on the right, is tied to x, but then the first bit, which is the one on the there's yeah. Why am I getting what is this bit order nonsense? Mm, let me quickly see if I can figure this out. If not, then it's whatever, right? But then I oh, because Alice and Bob, because this is wait no. But then which one is Alice's, which one is Bob? Does it matter? It doesn't, right? So then a no shouldn't. So a so if I get 0, 1, then I should be applying X. But then that means I need a condition on the first bit to apply X. So I don't know why I'm a condition on the second bit. I mean I know the result is right. You know what? Yeah, in the interest of time, let me finish and then we go back to fix all the bit order things. Or maybe if I stare at this long enough, I will see what is going on here. Okay, so now entanglement swapping. Basically we do the same thing as before. We have 4 qubits because they are EPRs. Okay, so Alice has the first qubit, Charlie has the next two, and then Bob has the last one. Okay, so Charlie has there are two classical, bits because Charlie needs to measure and store the result somewhere, and then we do the same successful checking. We also have classical register to check if our result is successful. Okay, so we start with the quantum circuit, basically all the qubits and all the classical bits. We prepare EPRs, which is the same as before. That we prepare 2 EPRs, and then we say that okay, now the 2 players have their operations. So Charlie does do this and do that. Yeah, okay. So now Charlie basically does a basically anywhere like from here up to here, right? Like this entire thing is Charlie's. So basically, he does a. I wonder if my bit order issue comes from this, or if it actually just doesn't matter at all. I don't know. Yeah. Um. Yeah, I think that is because when I act on this, this were. No, but that makes no sense. Yeah, I think that is because this is actually the like my circuit doesn't match because this I'm saying this is acting on the second, like acting on this, but then because bit order issues, this is actually a third qubit. Like I'm counting, I don't know if I'm counting from left or from right, so I need to be a little bit more consistent. But anyways, yeah. So let's say if I had this, then the math checks out, and then this is a for my notes. Okay, so basically, anyways, so Charlie does his operations on his qubit and on these classical bits, and then Alice basically also does her thing, as before, on on her qubit and on these classical things, and then after this, uh, this wire and this wire should form an EPR. So we check if that is true. By basically, well, there are kind of 2 ways to check. One is to just measure the entire thing and see if we get about half 0, 0 and half 1, 1, right? But turns out that that is not the perfect way to check, because that does not rule out this other state over here. Yeah, like 0, 0 minus 1, 1 will give you a sub-measurement outcome. So instead of that, we actually try to undo the EPR pair and measure, and if we get 0, 0, then we know that our result is correct. So we undo the EPR by doing this and this, then I should get 0, 0. So, and we check, and yes, the result here is 0, 0, which means my thing is successful. I mean, the bit order thing ends up checking out. So I must have, so maybe I got lucky and you fix that. Yeah. Okay, finally, the 5-qubit code. This part, I think I was a lot more careful about bit order. So luckily, I don't think I will have the same confusion here. Okay, and seems like we are like 15 minutes in only. And we also wasted like, wasted. We also like, was not very, how should I say it? What's the word? Like we also post a lot. So I think I might actually be able to finish the first part in half an hour, which is, I guess, good, because then I have like 40 minutes for this. Okay, so basically we'll cover this specific homework problem. So let me see if I can quickly pull up the homework problem for the, let me see, yeah, let me do this, just so I can pull up the homework problem without leaking everything. So let me see, where is the homework problem here? I feel I'm actually very blind. What is this? I know why can I not find a message? I'm actually tilted. What is this? Sorry, I'm just trying to find the homework problem. Okay, I found it. So download and then open on with browser, close Slack, and share screen again. Yeah. Wait, what is? Oh, this is the copy. Yeah, I was looking at my camera and getting confused. Okay, so basically we are going to cover this homework problem here, which is a 5-qubit code. Basically that quantum error correcting code. I don't know how much theory should I go into. Maybe I would just assume that for the sake of lecture, maybe I would just assume that the I mean, this is the students' last homework, so they probably know about it already. But yeah, we want to basically prove this that this corrects all single qubit errors. So let's go. Okay. A So basically, we want to first do part a what is it called? Yeah, we want to do part 5 and part 3. So we want to do syndrome measurement and we want to do correction. Okay, so for syndrome measurement, we want to say, like, given the Pauli operator, we want to measure with respect to its eigenspaces. Okay, and then we want to build towards the actual error correction, which is where we start with random state, we encode into a 5-qubit code, and then we apply a single qubit error, and then we do correction. And then we decode and hope to recover the initial state. That is our goal for the rest of the lecture, besides fixing my bit order issues. Okay, so remember this from homework because I just pulled it up just now. Basically the encoding of 0 is this, encoding of 1 is this. Okay, and we basically just transcribe this, nothing exciting yet. Basically, we'll plus, all 5 zeros, and this is this, and stuff like that. And for minus, I just put a minus in front. And basically, the same goes for the other thing. So this is this, yeah? Okay, and then we convert them to vectors. Basically, nothing exciting is happening. I might want to run this, yeah? And then basically you convert this to a vector, but nothing exciting has happened yet, just boilerplate parsing. But basically I want to say that, so now I want to say this is, well, this is actually, I have 5 qubits, so this is actually a 32-dimensional space, right? Because 2 to the 5 is 32. So this is actually a 32-dimensional vector, and I claim that this is this. So now let me tell you why is that the case, or what am I doing parsing wise. So first of all, I just check if the first bit is, if the first thing is plus sign. If it is, then it's 1. Otherwise, it's -1. That's a sign. And the value is, well, I need to do reverse because everything is because the bit order thing that I was talking about earlier. And then I need to cast the thing to integer. Okay, so this is a bit order thing. And then I need to turn each of these terms into a what is it called, into a vector, into a standard basis vector. So this is kind of what I do. Maybe I can quickly demo this. So if I do numpy.I, let's say, I don't know, 6, then this is going to give you a 6x6 unitary, yeah, the identity matrix. So if let's say if I index like this, then I'm going to get E2, right? I'm going to get the second, this is 0 index. I'm going to get the second standard basis, the second standard basis element, yeah? So this is basically how you get a standard basis. And this is kind of what I do here. Basically, I just say that, okay, I first figure out what number is this, and I get the corresponding standard basis element, and then I multiply a plus or minus. And then cat0L is basically just, I add them all together. So I parse each of them, and I add them all together, and then I multiply by this quarter overall. That is all there is to it. But if you guys did not catch that, that is no big deal either. All you need to know is that, well, there are, 16 things here, right? 1, 2, 3, 4. 10 plus 6 here, 16. And if you count here, 3, 6, 9, 12, 13, 14, 15, 16. So basically, it's like each of these corresponds to one of these. So it's just an identity check, and this is basically just this in actual vector form. Okay. I want snack. Do I have? So I did grocery this morning. I bought a bunch of snacks, and I want to start eating it. I have beef jerky, right? Yeah. Yes, I have beef jerky. Yes. Sorry. Oh wow! It actually smells very, very beef jerky-ish. I don't think my desk is very, very clean, but I feel like I will just dump the thing on my desk anyways because I'm lazy. Okay, so where am I? I promise I won't do it on the actual lecture. But yeah, okay. So yeah, in general, it's hard to write down a encoding circuit for quantum error correcting code. But like to write down the actual correct circuit. But right now, if I just want something that is good enough for lecture purposes, that's not as hard. So you want to write down a 5-qubit unitary that maps this to this and this to this, yeah? Then this is kind of a good enough encoding. So that means that I want a 0th column to contain this, and I want the first column to contain this, yeah? And for this to be unitary, you need to fill in the other columns in a way that they form of normal basis. And here's the code. Basically, this is just giving me the orthonormal thing, and I just kind of stack the vectors. So first column is this, second column is this, other columns are orthonormal. Decoding is because this is unitary, so decoding is just conjugate transpose, which we know and love. Yeah. Okay. So yeah, maybe I should stop eating. This takes a lot more time to chew than I thought. Okay. So syndrome measurement. Basically I'll just show this. So basically for syndrome measurement, basically the idea is that you have some syndrome that look kind of like this. You want to measure its eigenvalue. So how it goes is basically like this. The first qubit you do nothing here, yeah. And second qubit it is X. So the so you want to so this is kind of a circuit to kind of read out the error here, and then you do nothing, and then this X. So you read out the error here, and then you just do a CNOT. So this is kind of your error syndrome, and then you measure it. So this is, I mean, this is kind of homework exercise, but basically this is just kind of how to read out a single syndrome. I mean, of course, like five, this, yeah, I mean, the number is maybe also clear that you have data, you have one, you need one NCR to do it, of course, and then you have somewhere new store result. Okay, so now we want to measure all the syndromes. So particularly, you want to measure this, and that. Okay, turns out that it's not hard either. So basically, I just say that, okay, I have a quantum circuit, and then I probably want to say the sizes, right? So I want to say what? And a third length of ancilla, because it's good for code to be self-documenting, yeah? Even though I also have it below. But anyways, yeah. So I have it's 5 qubit code. So my data is of course 5 qubits. I'm measuring 5 syndromes. So I have, classical yeah, so this is 5, and I also need 5 here because yeah, I need somewhere to store it before I measure it. Yeah. Okay, so what I do here is basically, okay, I have this, and then for all 5 of these, I just compose, basically, I measure one syndrome. You know, I, I mean, this is kind of, I hope it's self-explanatory, but basically how it goes is that I just, I just run this, right, on the correct qubits. So the data, the ancilla, and then the where do you want to store result, and then I put one of these there, yeah. And then how this gets embedded in the overall circuit. So basically, this thing uses the entire data, and then by the way, like this is what is it called? Like this is redundant, I know, but I think this is just kind of how the library works. So once you have this part figured out, this part should just just kind of copy this into this. I mean, these are both quantum, so you need to kind of append them together. So this is also some strange part of this library. Yeah. Okay, so then basically let's just draw it and see if it, yeah. So I have this, I measure one syndrome, I measure the next one, measure, and then 4, and then 5. So this is basically kind of what it is. It's basically just, you start with this and you just have 5 copies of it. So nothing super exciting yet. Just write a loop, and we know how to write loops because we're programmers. Yeah. Okay. So now we can measure syndromes. Now we need to do corrections. Okay, so basically, well, if we want to correct, okay, so there are like more clever real ways to do it, but then because just for the sake of lecture demo, since there are only 15 possible single qubit errors, because you have only 3 possible Pauli errors, x, y, or z, and then you have 5 qubits, so 3 times 5 is 15. Because there are only 15, so we just hardwire all of them for now, for the sake of the for the sake of the demo for the lecture. Yeah, so we begin by writing down which Pauli error corresponds to which syndrome. So for example, if there is XZ error on the third wire, well, it's just, yeah, maybe let's start with this easier case. Yeah, is there a way to collapse this? There should be, right? How do I collapse? Is there? Oh, perfect. Yeah, I've collapsed this as well. Collapse that, so we can look at this. Okay, let's start with an easier case. So if I have X on the first wire, then well, what do I get? Well, this is not going to detect X here. This three I'm not going to detect, but this Z will detect X, and this Z will also detect this X. So I would expect 0, 0, 0, 1, 1. Yeah, and that is what I get. And similarly, if I move it onto a second wire, then what would I get? Well, I will get this is going to detect, so I get 1, 0, 0, 0, 1. Yeah, and that is what I get here as well. And how about Z error? Well, Z error is a it is I'm going to get 10100. Yeah. So this is, I mean, to fill is actually an exercise to fill it in, but hopefully not too hard. And for XZ error, so for Y we just write as XZ, but either way is fine. So if you have XZ error, then it is going to flip all four of these. Yeah. So get 10111. Yeah. And then that is what I mean by, okay, if you have 3, then it is going to have 11101. Yeah. So this is kind of how this should work. Okay, so now with this, we can kind of just look through all possible 15 errors and correct all of them. So let me show you. So we start with a quantum circuit, and then we consider all possible errors. So I have a product of, all possible errors and on all possible locations. I say that, okay, this is this, right? So basically, and then I turn this into an actual number because I need to, because because this is a string, but Qiskit wants to interpret this entire thing as a base 2 number. So that's what I do here. I basically just turn this into an integer value, because bit ordering I also need to reverse it. Yeah. Okay, and then I say that, well, if my error, if my syndrome matches this, then I have an X error on this wire, then I need to correct it. Otherwise, if it matches, yeah, I mean, this is just kind of reacting to the errors and correcting all of them. So let me just show this to you, yeah? I mean, the circuit should look like this. Basically, you have 15 possible errors, and all of them have a specific syndrome. So we just kind of do this reverse lookup by saying that, okay, if my syndrome is this magic number, then I mean, if we expand this in base 2, then you will get you get like one of these. If it's one of these, then we just correct it. Yeah. So this is, I mean, sorry if this is like terrible explanation, but it's kind of like this. Yeah. Okay. So, anyways, yeah. So we pretty much have everything now, yeah? Because we have syndrome measurements, and then we can also look at the syndrome and apply the corresponding corrections. So now we just kind of, I guess I can also keep using the excuses earlier that any terrible explanation is because this is a programming lecture and not a actual theory lecture. Oh, that's such a terrible explanation. But anyways, yeah. So quantum QC is a quantum error correction. So error correction experiment. Um, I start with the 5 qubits because we are doing 5 qubit code, and then we have Ancilla, which is working space, like where do we store our syndromes and where do we store them in a quantum way, and then where do we store them after measuring. And this success thing is as before. Yeah. Okay. So quantum circuit, that kind of a uses often. Okay. Random input as before. Yeah. And then I do encode, and then I apply random error by saying that, okay, I pick a random wire, I pick a random unitary, and I apply the error on the wire, and I do the error correction, which is a I measure all the syndromes, which is what I wrote earlier, and then I do a correction, which is also what I wrote earlier. So at this point, this error should have gone away. So now we decode the QEC and hope to get the. So after we decode, we are expecting the same random input as before, right? So that is what we are. Is there a random space here, or is that just enter? Wow, this random space is funny. Yeah, okay, so we just undo our random unitaries here and see if we have the 0 qubit. So that is our success criterion. Okay, so this looks a little bit scary, but basically this is kind of what I was just saying earlier. To prepare a random input, you encode the entire thing into error correcting code. You have a random error. It chooses this wire this time. Why not? And then you measure all 5 syndromes. So 1, 2, 3, 4, 5. Yeah. And then you do this, and then you need to, after you have the syndrome, you need to correct the error. So basically, you just do this kind of reverse lookup brute force hardwire thing by saying that, yeah, if this is this, then it must have been this error. If this is this, then it must have been this error and stuff like that. So you just kind of correct all of it. And one thing that I kind of brushed under a rug, but I hope the lecture has covered, is that I'm only addressing Pauli errors, but this is actually arbitrary unitary. So this is actually a sum of possible Paulis. But this works for theory reasons I won't go too deeply into. So now my error has been corrected. I decode and I do my preparation. I undo this prep. So here I should be expecting 0 here. Measure to see if it's 0. Yeah. So that is the QEC. So that works. And that's supposed to be at the end of the lecture. And I feel like, I don't know, I was originally thinking that I have too much material. That this would be way over time. I guess not, right? Mhm. Because it's been like what, less than 75 minutes since the beginning of the stream, and what was I saying? A and we kind of post a lot during the lecture, so I don't know. Anyways, yeah. Okay, so anyways, next let me why is this grayed out? This should not be grayed out, right? I actually use them. But wait, this is so nice. Anyways, I missed FF14. Uh, probably FF14 is getting good. Maybe I should go back to a game. This jerky is also good. Yeah, so I guess my flow, right? Let's try to fix the bit order thing before we call it a day. Hmm. So what is going on here? Well, I feel it's just the same bit order issue again, right? Because like, how should I say this? Like, okay, so this is quote unquote the first wire, but then if it's the first wire, then it should be the bottom wire on the diagram, and this is just really bad because like when you're staring at this, you expect this to be on the first wire, like you expect the left wire to be on the top. So it's like I don't know. I feel like there's just so much like stuff that is just inconsistent, and whichever way we solve it, like the things are going to look terrible. Because I do want at least this wire to be on the top. So okay, fine. So let's say if at least this wire is on the top, so the left wire is on the top, and what happens, right? If the left wire is on the top, then then when I do a measurement, I will have to reverse the measurement out. I have to just manually reverse the measurement outcome at the end, right? So what happens? Let's see. Well, I guess the convention is also unclear, but I can just say edits always send exact. Edits always apply exact, right? Hmm. Yeah, let's say edits always apply exact. So this is actually said. Yeah. And then pop does this, yeah. Then then I should have a flip. I don't know where. Mm, EPR, and then at least decide to apply that. And then a to do this, you are going to get this, yeah. Mm, hmm. Oh, maybe I should say this. Based on the calculation above, Bob's measurement outcome will be a ZX, right? I think that's the missing piece, yeah. Um, right? Yeah, be ZX. Yeah, but then this is a okay, and then I should just write okay a correct due to the measurement outcome uh 01 actually corresponds to a cat 10 due to a bit order. Uh, That is a maybe I should just say this. And then that is what? That is a z equal to 1 and x equal to 0. Which is what we want, yeah, which is correct. Right? Yeah, because this is okay. Yeah, so that is a missing piece. Now the bit order issue is fixed here. Now let's actually also look at interpretation to see what is wrong with the bit order thing. As for this, I feel like I should play some video games, but I don't know which one to stream. I feel like it's either Silkstone or a what is it called? So it's just one more beef jerky. Feel like I actually did have lunch. I don't know why am I so hungry. I've been eating so much in the last like 3 days. Yeah. But yeah, what was I saying? Yeah. It's either still song or be rising probably. Um, kind of dumb-ish with World of Warcraft. We'll see. Yeah. So what's wrong with this? Let's see. Hmm. First bit is used to control Z. Second bit is used to control X. Um. Oh, maybe that's all that. Hmm. Oh, sure. As long as I'm consistent, I'm fine, right? Because I'm not reading the. I'm never interpreting the entire 2-bit value. So actual bit order doesn't matter. As long as as long as this goes down here, and then the first bit is used to control Z, which is the case, that'll be fine. And same here. Okay. So let's see if that's actually being done here. Yeah, so I think here there's actually just no byte order issue, like bit order issues at all, right? I mean, this is basically just the first bit being control Z, second bit control X, and this is exactly what it should be. And then the first bit measures in first, second bit measures in second. Um, -1 index / 2 index issue. Um, anyway, so we have this, we have that, and then here do we? Yeah, okay. So I think everything works. So I guess now the remaining questions. Oh, wait, I still have entanglement swapping. Yeah, let's figure out what is wrong with entanglement swapping as well. Yeah, I'm actually going to finish. No, I want something else. I feel I've had enough beef jerkies. Maybe coconut chips? I'm sure, except you guys, Yeah. How do I open this? Do I want to grab a Caesar? Do I have to grab a Caesar? I kind of want to. Okay, perfect. Now, how does this taste? I hope it tastes good. Look at. Oh, it smells so nice. I promise I did have lunch. My mic is not good enough, I know, so you guys cannot hear it, which is both good and bad. Okay. Oh, it's the same idea, right? That as long as I'm never reading this out as I'm never interpreting this as a what is it called? As a too big quantity. Like for all intents and purposes, these are just two separate wires. And because of that, as long as I'm consistent, I'm fine. And that is, I think, what is going on. Yeah, that a mm, oh, except this is funny, right? So I want to say what? I want to say in the first bit, I want control on the first bit to do that. This is what I'm doing. Yeah, control on the first bit do that. Control on the second bit do X. Yeah, okay. Yeah, I feel like the other way to do it is to say that from here, I switch order here. I think that this, um, that forcing this to measure in the other into other class of it, and that would also do it. But there's no point. Like, yeah, this is might as well just think of this as two separate wires. And if that's the case, then it doesn't really matter. Yeah, as long as these two are the same, like as long as these two are consistent, it will work. Yeah, so I guess we are actually done with the lecture thing. Good. Then I guess I don't know. I will probably be back for gaming later today. Um, after I have a little bit more snacks and a I don't know, or I'll be back of grading or something. Yeah. Anyways, thank you all. I will see you soon. I need to figure out what am I doing later. Hopefully, probably today, unless I go to sleep and just sleep for a long time, then tomorrow. But yeah, I don't know. We'll see. Yep. Thank you.